Today, we are very happy to have Jiafei from the School of Computing, National University of Singapore, which he will join soon. So he's an incoming assistant professor there. He completed his Ph.D. in computer science and engineering at the University of Washington, where he was advised by Professor Dieter Fox and Ranjay Krishna. His work lies at the intersection of robotics and computer vision with a focus on robotics foundation models, particularly scalable data collection and generation, grounding vision language models in robotic reasoning, and improving robust generalization in robot learning. His research has been featured in MIT Technology Review, GeekWire, VentureBeat, and BusinessWire, and has appeared at top AI and robotics venues, including ICLR, ICML, RSS, CoRL, ECCV, IJCAI, among others. His honors are the Best Paper Award at Ubiquitous Robots 2023, the Best Paper Award at CoRL RememberRL Workshop 2025, and a Spotlight Award at ICLR 2024. We are so happy to have you here, Jiafei. The stage is yours.
Yeah, thank you. Thank you for inviting me. Let me share my screen.
Yeah.
Can folks see my screen? No, maybe not that screen,
Yes.
but screen.
Yes. Now. Yeah.
Okay. Oh wait, sorry. I need to turn off the recording thing. Sorry, just 1 second. Yeah, so I think today's talk is going to be slightly different, although the title was saying something else, and the extra sort of says, I'm going to talk about three areas. But I realized yesterday, that if I do that, I'm not going to be able to finish in half an hour. It's going to probably take like 2 hours or so. And there's a lot of like exciting work that goes beyond this. So I thought of like maybe the one word that I really want to share, and it's something that we released last week, and really, got the community really excited about it. And I think this is a great venue to sort of, be the first to sort of talk a bit about this work that we have done. So today I'm going to talk about this work called MolmoAct2, which is the action reasoning model for real-world deployment. So more specifically. So I think the motivation is really simple. I think machine learning has sort of, made tremendous progress beyond academic setting. So beyond the regular benchmark that you see companies care about. In today's context, AI and ML has sort of pushed, having agents that's able to write your emails, answering questions. You have, digital agent that's able to sort of assist you with all these digital tasks and even generating code for us, like especially for PhD students or like for anyone who work in this IT field, you have this agentic framework that's able to generate code for you, at work. So in many ways, I think AI has sort of, augmented the way we think and work in the digital world. But I think many of you here might agree with me there is a missing piece. And in that case, the missing piece here is the physical world. But we could sort of imagine how AI system could potentially help us with, our everyday household chores, for example, folding clothes, assistive care for elderly, or even just enhancing the quality of life in general. And I would like to sort of argue that the missing link to sort of bring AI into the physical world is robotics. But where are we right now with that goal? I think robotics has sort of moved pretty fast in the past decade, but I would still argue that most robots today live comfortably in a factory. They are sort of built to do very specialized tasks, and oftentimes they are operating under this highly structured environment that is pre-programmed by human experts ahead of time. But that's not what we want, right? We want a future where robots is able to move into our everyday home. In fact, that has been the vision that has been sold to us, for at least decades. And we want this robot to be able to help us to do some of these mundane chores that drains our time. But if you look at homes versus a factory, the narrative is very different. Homes is much unstructured, it's more messy, it's always changing. There's humans around, correct? So in that case, we need a new form of robot autonomy. And in this context, we need robots that's no longer caged. We need robots, hardware that's able to sort of, coexist with humans in the same living condition. And then we want the robot to be able to exhibit some of this general purpose behavior that will essentially work from one home to another without too much, adaptation. So a natural solution sort of arise for robotics. We have seen the success of ChatGPT and all these large language model, and we realize that there's three key aspects that leads to this success, which is to just scale more data, build bigger model, and training broader skills. And I think in fact that's what people in the robotics community have sort of also converged towards a common recipe for building robotics foundation model. And such model takes in vision, language, and action from the robot and is trained to predict the next action on top of a large language model or vision language model backbone. And this leads to a whole new class of model class, which is what I call as a vision language action model. And more noticeably, I think Google has a track record setting the earlier, examples of such models with their RTX series, and then now following by the Gemini Robotics and Physical Intelligence, which is a startup that came out of Google. Also focus on developing some of these general purpose robot intelligence through that generalist models such as Pi. But there is a problem with today's generalist model because we know one thing for sure, which is that everyone here uses ChatGPT, and we know that LLMs are pretty steerable, which means that you are able to sort of control the way you sort of prompt the LLM, and the LLM will be able to adapt itself to give a new objective, and this could be done in more technical approach such as in context learning. But in robotics, even though we follow this paradigm of scaling data, training broader skills, adding more compute, we don't get that. So for example, if you look at state-of-the-art model, for example, physical intelligence, Pi 0.5, the language instruction is pretty straightforward. Place the fruits in between the two places. But you can realize that actually the robot does the action pretty well. It picks up the object and then it moves and place it down somewhere. But it's definitely not in between the two places. So why is this the problem? Because there exists a gap between the semantic understanding of the model versus the action that the model is able to take. And this is something that does not happen in a language model because if you prompt ChatGPT something else, ChatGPT will be able to sort of easily adapt to that. So why is VLA sort of struggles with this task that's so trivial? I think it comes down fundamentally to two problems. The first problem is that we train these VLA models on top of a base VLM model, which learns vision language alignment. And then in that case, if the VLM model inherently doesn't even know what does it mean to be in between the two plates, the VLA model will inherit the limitation from the VLM and will not be able to do that. And that's true because if you ask ChatGPT, you ask Gemini, you ask open source model like Quen, what does it mean to be placing the fruit in between or localize what it means to be in between the two places. All this model can do is to give you bounding box of the object itself. Some of them give you a more fine-grained bounding box, and that's pretty much about it. And also the second reason is because the way that today's models are trained end-to-end, trying to go from observation to action, hence there's a lack of this kind of deeper connection between the high-level semantics that's captured in the VLM, going through into the action that the VLA is actually learned to predict. So to address this, we need to address these two shortcomings. And to address the first shortcoming, which is that VLM struggles from language conditioned spatial affordance prediction. What do I mean by spatial affordance prediction? So in the robotics context of spatial affordance prediction in general, it means that if you ask VLM, to give me the affordance of how do I pick up the banana, it should ideally give you a 6-dot graph pose, telling you how you should move that robot to that position. And if you ask it to place the banana somewhere, it should give you a region in space or like also on the image observation, telling you where to sort of locate and place that banana so that it's stable. And this is pretty straightforward why today's VLMs cannot do it because they are not trained with such affordance data. Oftentimes they're trained with this object-centric data with like detection or like segmentation mask. So they have no idea how do you sort of interact. And affordance is basically more task relevant, right? So that's the first challenge. So to address that, we introduced a robot point, which is like the first vision language model that's sort of designed for this specific goal of spatial affordance prediction in the open world setting. And what does that mean? It means that if you give the VLM, which our VLM robot point, this observation and the exact same language instruction, robot point should return you a set of normalized coordinates. And if you plot this coordinate on the image observation of what the robot sees, it basically points to the region that the language is referring to. So by doing so, we actually introduce a new perspective of looking at spatial reasoning, which is rather than treating it as a vague semantic capability, we reframe it as a fine-grained language condition to delocalization task that works on open world setting. So how do we do that? I think it's not trivial to be able to build a VLM that's able to sort of generalize this new capability in an open world environment because you need a huge amount of data to actually do that. And if you want to manually annotate some of this affordance data with human labels, it's not going to be scalable because imagine every object or every spatial affordance point, you have to annotate a point, come up with a language instruction, and then generate the prompt. So it's not scalable. So the way we did it was that we designed this entire data generation pipeline purely from simulation to obtain this spatial affordance label. So we first use NVIDIA scene synthesizer to generate a bunch of these programmatically generated 3D environments in household settings, and we populate them with a bunch of 3D assets that's widely available. And then the idea here is that because you know these assets and you know this privileged information, you could draw out some form of object reference between objects and even relative to certain objects. And then you create these annotation points on the object itself. So that gives you the affordance of how do you sort of interact with these objects. And then for those contexts of free space affordance, which is like, for example, on the left, inside, between, above, these are all ambiguous concepts of spatial reasoning, correct? So in that case, what we did was that we take the points of the annotator object relative to the other objects that's in the 3D scene, we remove the object while keeping the annotation points there, and then redefining the spatial relations between the other object that exists, and we re-render the entire scene to give you this data or this examples of observations together with these annotator points as some free space. And that gives you our free space spatial affordance data set that you could actually essentially take our affordance data set to train any VLMs today and give you this new ability of spatial affordance prediction. So what can you do with RoboPoint? There's many things you can do with RoboPoint, right? So the first thing, obviously, you want to use it to localize a target object that you want to sort of act upon. And in this case, for example, I want to pick up the orange. You prompt RoboPoint. RoboPoint will give you that points on these objects. And then all you need to do is to either have a pre-existing policy that you can condition your points on, or you could use a grass network that propose a bunch of grass candidate and use motion planner to move the robot to that grass pin post. But the difficult part is how do you do it in a way that's placing the orange on the bottom step. So previously in robotics, this requires a lot of heuristic design or hand engineering to figure out what it even means to be at the bottom step. But with RoboPoint, all you need to do is just prompt RoboPoint, and then it give you these 2D points, and you just use that 2D points to condition your action prediction. And beyond that, I think what's really fascinating about RoboPoint is that it actually generalized beyond the kitchen or like tabletop setting that it was trained on. So this was me driving down Bellevue, and my partner took a picture of this, and I asked RoboPoint, how do I get to the carpool lane? And what RoboPoint tells me is that it will tell me that because it's a general purpose VLM, it will tell you that go to the left of the leftmost car. And then if you ask it to prompt it to give you the points, you realize that at every frame or in this video sequence, it follows that kind of temporal consistency of locating the exact region, even though we have not trained with any video data. So that's really impressive about RoboPoint. And what's more interesting is that with RoboPoint, I think we enable some of these frontier VLMs that people are using today with this new set of capability, which is language conditioned 2D pointing. And on a separate paper that I introduced called Point Arena, we actually systematically study this phenomenon. So we found that actually before the release of RoboPoint, when all these models, like frontier models like Gemini, GPT, when you evaluate their pointing capability, you realize that they just basically hallucinate, and it's as close as good as to random guess. And then after we introduced RoboPoint, suddenly all this model develops that spatial pointing capability that we see today. And for those folks that works on robotics, pointing has also become a sort of a de facto ways of conditioning your policy. And in fact, I think NVIDIA has also implemented this in their hardware get starter kit so that anyone who wants could easily deploy RoboPoint out of the box on NVIDIA Jackson. I think that's the case here. So with this pointing, we are able to solve the first problem, which is to give VLM this capability of understanding spatial reasoning, and then sort of able to sort of localize, in the context of just now that task, what it means to be in between. And I do think that pointing is a great, intermediate representation to connect language to action. But can you go beyond pointing? Sorry, can you go beyond just pick and place tasks? So if I want a robot today, in this case, the robot here, to pour me a cup of coffee, and you ask RoboPoint to help you do that, RoboPoint will give you 2 points, but that's not going to solve the task. sure, you can use some as existing modular system, but it's going to be really tricky and hacky. So the way we think about this, the human does this very intuitively. We have a formulation of a plan that helps to guide and structure our action. We use some form of implicit depth to refine and sort of refine our actions. And lastly, we ground our reasoning process of actions in the physical world. So to do that, we introduce MolmoAct2, which is a generalist robotics foundation model from the Allen Institute of AI that does exactly what I just described. So when MolmoAct is given this task and the observation, MolmoAct first predicts a set of perception token, and when we try to decode this perception token, it gives you a depth map, which allows the model to have a sense of the 3D structure, and then it auto-regressively takes in that depth token and then predicts this visual reasoning trace token. And then when you try to, manifest or sort of like decode this visual reasoning trace token on the observation that the robot sees, it gives you a line sketching forward in time, telling you exactly what's the action that you should take by the robot. And then condition on that, MolmoAct then predicts the action tokens that could be used to decode and give you the necessary action to be able to solve the task. So with that, we introduce MolmoAct, and this is to the best of our knowledge the first fully open sourced reasoning action model that has open source in every aspect. So we open source the weight, we open source data, we open source model, and it can be fine tuned and trained and deployed onto many different embodiments. But then one of the interesting selling point, which is this kind of chain of thought style reasoning, is that we realize that today's context of training robotics foundation model just inherently lacks this kind of implicit reasoning supervision. And that lies in the way how these kind of data are being formatted. If you look at the largest data set in robotics that people have been using to train some of this robotics foundation model, which is called OpenX embodiment, you realize that the way they formulate this data set is just observation that the robot sees. You have some form of language instruction and prompts, and then the output is just textual outputs of various numbers that you could potentially encode and decode into actions using a tokenizer. The problem about this is that it results in multi-model representation that's pretty ungrounded and loosely connected. So how do we sort of close the gap that I showed in the early slides, which there's this spatial semantic gap? I think to close the gap, we need to provide more implicit reasoning supervision. And one of the important lessons we have learned from language model is this kind of intermediate reasoning. So people probably heard of chain of thoughts, which is very interesting idea whereby all you need to do is just ask the model to think step by step. The same model is able to have much better performance. But what is reasoning looks like for robotics, I think we cannot use language as a medium to solve reason because language is just fundamentally ambiguous to describe motion in space. How are you going to be able to describe a robot's motion or trajectory using natural language? That's not possible. So we need to be able to ground this entire reasoning process. And the way we sort of do it is by curating this new form of data set to provide this kind of grounded supervision. So for our data set, we take existing robot data set that also has the prompt of like what's the task that the robot is doing, what action it should take next, and together with the observation. But the difference is that MolmoAct will be able to sort of output, this kind of perception token, and then followed by this kind of visual reasoning trace token, and then following by this kind of action token. And and as I go through, you'll realize that a lot of these tokens are actually purely grounded into the physical world in one or another aspect. And so the way we do it is that we curate this data very interestingly. So for the visual reasoning trace token to sort of give a sketch forward in time, we use a RoboPoint or any of these pointing model that came out after to just point to the gripper. And then if you connect the trajectories together, and that will tell you, at this current time step, what's the next sequence of action that you should take represented in this kind of implicit visual sketch. And then you convert that into a reasoning token, and then that will be used in the vocabulary for training MolmoAct. And then for the perception token, which is that we want to provide some form of implicit 3D sensing, but we cannot rely on existing robot dataset because they just do not include any depth measurement during data collection. So to address that, we generate pseudo-depth supervision from RGB alone, and more concretely, what we do is that we pass all these RGB frames that people have already collected of robot data through a depth anything V2 to generate this kind of pseudo-depth map. And then we train a VQVAE on this kind of depth prediction. And the idea here is that for the learned latent code boot to serve as a perception token. So once the network has been trained, we will freeze the tokenizer, we will freeze the encoder itself, and then any new image that we want to encode, we can use def anything to sort of distill out the kind of pseudo def map, and then we pass into an encoder itself, and then that will give you the perception token that's required for us to actually annotate this data. And if you put this all together and you train a autoregressive transformer with a next token prediction and sort of pre-train at scale with the huge amount of data that we have that's open source, you will get MolmoAct2. And then this kind of autoregressively chaining this kind of reasoning token really helps to improve performance quite dramatically. So in the early stage of MolmoAct2, we want to evaluate its capability to deploy. And then one of the things that we evaluate is on this benchmark called SimplError, which the idea is that it mimics the training distribution or visual distribution of the data set that was used in pre-training by many of these frontier models. And we found that Momo is able to achieve one of the SOTA performance at that point in time. And then more importantly, we are able to sort of outperform many of these frontier models, like for example, Pi Zero back in the days, or NVIDIA Group 1.5, with using significantly less data. In fact, we are using like 20, 30 times less data than what they used for training their model. So it really shows about the quality of the data rather than the scale itself. And then one of the important questions that we want to investigate with MolmoAct is that did MolmoAct actually breach that spatial semantic action gap that I described previously? I think many people does not really sort of see why this is important, but then the way we sort of look at how we understand this is to conduct a series of ablation on this large scale pre-trained model, and then really try to have a better understanding whether have that gap been closed, and is the way that we are doing with this kind of intermediate interface of the visual trace able to solve this problem. So the first thing we want to evaluate is that did the VLA actually retain its general semantic reasoning capability? So can you say that the model is reasoning if it doesn't even differentiate a cat from a dog when you feed in the observation? Correct. So that's the first thing we did. So we take all the VLMs that's out there, not all, so we take some of them well-known VLMs, VLAs out there, and we look at what is the original VLM that they were trained on. And then because they are sort of like full fine-tuned or trained on top of it, inherently it should preserve the kind of general semantic knowledge that the VLM is capable of. And that's not the truth. That's counterintuitive to the result, which is that we found that most of these VLA model, after they have been adapted to become a VLA, they lose a lot of their general knowledge capability. They lose their knowledge in multimodal understanding. They lose their ability in visual structure reasoning. And then you could see the difference here, right, between the base VLM and the VLA model that you train on. The VLM still preserve all this knowledge, but then once you train it to become VLA, it doesn't. But Momo, on the other hand, sort of maintains that general multimodal reasoning capability from its base VLM. So that's the first thing we investigate. And then the second thing we want to investigate is, how much does this sort of intermediate interface in the form of a sketch or a line sort of represents a human interpretability medium. So in this case, the way we did it is that we give a lot of observations to online annotators, and the idea here is that we did a blind evaluation whereby the users can come up with any arbitrary instructions. And what MolmoAct does is that you will draw this kind of visual sketch. So did the other baselines, and then we ask humans to rank, how good they think that the visual sketch aligns with the natural language instruction. And we found that over 300 online participants through this blind evaluation, MolmoAct is able to actually have a really high ELO rating, which people use to do this kind of preference evaluation, which says that MolmoAct is able to ground human instruction into this kind of visual reasoning trace, which could serve as a proxy of reasoning. And then the last step we want to investigate is that, since now humans can use natural language to come up with this kind of visual reasoning traces that aligns with human intent, how well does the generalist model, in our case MolmoAct, actually follows this kind of visual sketch? And if it does, then we can use this to actually do higher order reasoning. So one thing we test is that, okay, now if you give an arbitrary language instruction, which is to put this toy on the coaster, and there's three coasters there, MolmoAct will generate this kind of visual sketch telling you the certainty of which coaster you want to go to. And you realize the last frame actually wants to go to the coaster at the bottom. But as a human, I could use a pen, and not use a pen, but I could potentially sketch on the observation a different line and feed that into the model. And then now MolmoAct is able to steer its objective towards that. And more interestingly, now you're able to unlock some of these new abilities. So for example, in this task, we want to put the apple next to the Coke can. Without this ability to use Momo as visual reasoning trace steering, to sort of add a constraint to avoid collision, the base policy will just ran into that wall that we actually set there. But as you can see now with Momo as ability to sort of taking instruction and generate this kind of alternative trace for the action to follow faithfully, now you're able to sort of solve some of these constraint problems whereby to prevent collision. And obviously, we also evaluate how well does the action aligns with the human, aligns with the language instructions versus also aligning with the visual reasoning sketch. So in conclusion, I think MolmoAct is able to sort of be steered by this kind of visual reasoning trace. I think the impact of this new paradigm of training robotics foundation model or VLA in short is through this reasoning in space paradigm, right? So more and more work sort of follows suit after us. That sort of adapted this similar idea. So Google's Gemini Robotics 1.5 built on top of the same idea. And then VLA models that does navigation also uses visual reasoning trace to condition its action. And there's more work that's all built on top of it. And since it's a fully open source effort with a really strong academic focus, our checkpoint has sort of been downloaded and released over, downloaded over 280,000 times in total since it was released last year, August. So that's with MolmoAct2. And I think it really sort of sets the tone for the first example of a fully open sourced VLA model that sort of really provides that interpretability for you to sort of diagnose the whole model end to end. Because we are training fully on open source language model, vision language model, so everything in this whole pipeline is fully open to everyone. But there is still a fundamental problem because we want to build a really powerful and high performant robotics foundation model for the community to sort of build on top of it. And as much as MolmoAct2 is pretty great, there's still a lot of limitations. So limitations, for example, is kind of slow because of these reasoning tokens. It's not able to sort of deploy out of the box without efficient fine tuning. So these are some of the problems that sort of hinders the community to sort of build towards. And to be honest, with a lot of these rapid advances in robotics foundation model and all this whole new line of work on world model, you realize that, despite the fact that there is so many models out there, but there's only one or two models that people actually find really useful to actually deploy for real world use case. Oh. So one of the example will be price model. There is some of this I think there's some music. So one example of this Pice model, which is able to solve, be quickly adapt to many different embodiment. People use it to adapt it to drones. People use it to adapt it to, quick operations. So there's a lot of real world use case, and people are building on top of it. So, which is good because I think that's how we sort of pushes the field towards, towards that ChatGPT moment of robotics, right? But I think one thing that I'd like to sort of argue here, moving towards the next section of the talk is that, for ChatGPT to reach that ChatGPT moments of, ChatGPT, there's a lot of things that happen before that. And a lot of these things happen because of the effort of open source and openness. So I think the same paradigm should follow for robotics. So for example, if I don't think there'll be a ChatGPT moment, for ChatGPT if there's no things like Torch, there's no things like Cafe or like, ImageNet, Common Crawl, Transformer, or any of these kind of open source model that sort of propels things forward in research. So I think in that notion, I think in order for us to reach that ChatGPT moment of robotics, we should also think about how do we build some of these open tools, open data set, and open models for people to sort of use and build on top of it. So using the what I call this model openness framework, you can actually look at some of these generalist models today that's out there by these kind of large startups. You realize that many of these falls under more of an open tool rather than open model. So physical intelligence model falls under open model and it's one of the most used generalist models out there by the community. But I think we are really missing one important piece, which is open science. Because if people are not able to understand what is going down underneath the hood, then they're not able to sort of, further build better models, new tools, or new data sets to sort of improve and push the field forward. So I think with that idea in mind, that's something that we think about when we're trying to build the next generation of MolmoAct. And also another problem that's sort of bothering us a lot is that many of these models today, or actually there's a lot of VLA model that came out every day, still requires some form of fine tuning. So you need to have a policy, also you need to have a task that you want to solve, and then you can't deploy your checkpoint out of the box. You actually need to collect some data and then fine tune the model. And if it doesn't work, collect more data, fine tune the model. So the idea here is that, this is good because it helps you to customize the model to become a specialized model for deployment. But at the same time, you also want to be able to deploy some of these generalist models out of the box. So the question is, can we get such generalist model to work out of the box? So with that, we introduced MolmoAct2, which is the second iteration of MolmoAct with this exact goal in mind, which is to come up with a model that could potentially allow the community to sort of, deploy it out of the box. And this is one example of what MolmoAct2 does. We are able to sort of set it up in a table setting, and then you can bring in a task. Sorry, and in this case, the task here is to fold tower. So we want the policy to be able to sort of, continuously doing these useful tasks, meaningful tasks. And I think a lot of times, what we see today with some of these VLA models is that it's still working on a lot of times on toy style kind of tasks, which is not that, the implication is not that strong for real world deployment. And for real world deployment, there's a lot of things that we also want to look into. For example, like folding this tower, you really want to make sure that the model is able to fold it pretty neatly and consistently doing this over and over and over again. So with that in mind, we built MolmoAct2, which is the action reasoning model iteration that's for real-world deployment. And we want to put this into wet labs, we want to put it into homes, we want people to deploy into coffee shops, and we want people to even deploy into laundromats and consistently improve on this model. So what's the difference between MolmoAct1 and MolmoAct2? Is that we basically reinvent and rethink through everything about how we build this generalist action reasoning model. So the way we do it is that we started with a VLM, which is Momo2, which is a fully open source vision language model from AI2. That's also built on top of an open source language model, which is OMO. And then the idea here is that we want you to be really strong for reasoning, for embodied reasoning specifically. So we actually train a variance of that called Momo2 ER. And then on top of that, we have two main stage of training. One is the pre-training stage where we learn basic action alignment. And then the post-training stage is that we train this pretty good action expert that's able to take noise and generate robot actions, but then still condition on the huge semantic knowledge that was trained during the pre-training phase. And then we also introduce a new way of connecting these kind of VLMs with the action expert so that you get this kind of new class of VLA model that's flow-based. So how do we train the VLM? So we didn't start with using Momo2, which is what we did with the first version of MolmoAct, and use that as a base VLM checkpoint. Because, as I say, there might be some capability that matters to robotics that might be missing. So the way we did it is that we actually further train MolmoAct2 with a bunch of reasoning datasets that focus mostly on embodied reasoning and even physical reasoning. And we found that with MolmoAct2 we are actually able to achieve some of this really high SOTA performance across a wide range of over 13 different benchmarks for embodied reasoning that companies like like OpenAI or Gemini, focus on evaluating their embodied reasoning models. And we are able to sort of surpass many of these models out there in this embodied reasoning capability. And then the next step is we do pre-training. So we pre-train the VLM into a VLA, and then we pre-train with a large amount of academic data set that's all fully open source. And we introduced two new data sets. One is MolmoAct's bimanual EM data set, and the other one is the SO100 and SO101 data set. I believe some of you might, also have that robot lying around. And the idea is that we also sort of use our own open fast tokenizer for training this pre-training stage, that we actually open source all the data that was used to train that tokenizer. So FAST is the tokenizer from physical intelligence, and they open source the weights, the checkpoints or the model for the tokenizer, but not the data set. So in this case, we open source also the data set that was used to train OpenFast. And the way we sort of do it is that we spend a huge amount of effort trying to curate high quality data sets so that the community can sort of benefit on top of it. People could either take it to, train their own robotics foundation model or have a better ways of like understanding and diagnostic what is actually goes into the model itself. So with that, we actually came up with a new setup to collect bimanual manipulation tasks for real world deployment. And then in this setup, this is constructed with using two EM arms, which is pretty cheap. So the whole setup costs about I think under $7,000. So anyone around the world could potentially build this setup. And then the idea here is that we provide fully open over 720 hours of high quality robot data that was collected in this setup across a diverse range of real world tasks. And when I mean real world tasks, you are looking at tasks like wiping the plate where the plate is actually dirty and you use sponge and soap to actually wipe it. And then at the same time, this is almost I think 100 times more than what MolmoAct2 data set that we collected in-house, which is only 22 hours. And beyond that, we also know that many people in the community or hobbyists that wants to have a taste of this robotics foundation model, they probably does not have expensive robots like the Yamams or even Franca. They might have something like SO100 or SO101. So we also take the liberty of scraping all this open source licensing data set from Hugging Face that consists of over 1,200 different diverse data sets of these low-cost robot arms. And at the same time, we also spend a huge amount of effort to re-annotate all the language annotations in this robot data set. And I think this is really important because you want the model to be able to take in diverse language instruction, and you don't want to be keep trying to prompt and testing different language instruction just to get the behavior that you want. So these are just some examples of some of these tasks that we have that's part of the data set. And you could see the difference between the original language instruction versus the instruction that we through our language annotation pipeline is able to generate contains much more rich, dense captioning of what the robot is actually doing. And we found that actually improved performance quite significantly. And also for the next stage of training to train the action expert so that MolmoAct is able to sort of, do action much better going from previously with MolmoAct2 doing purely autoregressive, now with a flow matching as a objective. So right now out there for a lot of these VLA models, there's different ways people sort of connect a VLM model to the VLA models. So for example, Physical Intelligence Pi uses Polygemma as their their action expert, which is an LLM, and then they try to do layer by layer connections. And then for models like, for example, Groot 1.5 or Groot, they follow the same architecture, which is that they will use a DIT, which is what mostly common use for generative model these days, with a flow matching objective. But then they use their hidden state from the last layer to sort of compress all the semantic capability from this VLM, and then using that to condition on learning action generation. And we found both, and we found through our experiment that both of these approaches is not that efficient to sort of retain that kind of semantic knowledge that you expect to sort of preserve in the VLM models, and then using that to sort of improve on your action prediction. So the way we did it was that instead of using hidden state, we used the K and V from the VLM, which is under the self-attention layer, and then we do layer by layer concatenations with the DIT action experts to better condition on the action generation rather than compressing it all into a single hidden state. And with that, we want to evaluate MolmoAct2's capability because it's still academic, research work, and we really want to see how good is MolmoAct in terms of performing under different circumstances. So the first thing we did was that we look into how well is MolmoAct2's capability to be deployed out of the box. What I mean by out of the box means that if you have a robot, and you have there's no like you don't need to fine tune, you don't need to collect any data. You could eventually just download the checkpoint, run MolmoAct, and see how well does it do. So one of the benchmark that came out from the Allen Institute of AI that looks into study this kind of out-of-box deployment with this kind of VLA model is called MolmoSpace. I think Jensen mentioned about this at GTC. And then based on our evaluation, MolmoAct is actually able to outperform many of these pretty strong baseline models, for example, Pi 0.5, which is also trained on Droid, LAP, which is from Princeton, and a lot of these other VLA models on this simulation environment that I talk about. And secondly, we also evaluated in the real world, looking at some of these generalist models that's out there that could potentially just deploy out of the box on a droid setup, which is a Franca robot. And we found that actually MolmoAct performs really well in terms of, following human instructions, getting this kind of task executed. So this task was never seen in training data. And then in fact, this task, I don't think anyone has collected data of this task in the original Droid dataset. So it's really purely out of distribution from what it's trained on. And based on a large scale evaluation, we found that our model is really able to perform pretty well on this Droid setup. And then also we also tested on SO100 and SO101 and realized that MolmoAct is actually doing pretty well on that too. And obviously, we want people to also take MolmoAct to be able to fine tune or effectively adapt to their new task or new embodiment that was not part of the training. So the way we did it is that we did a real world evaluation at scale. So we hired a third party company that is able to do blind evaluation for us. And then they collected a bunch of these real world data sets of doing some of these meaningful tasks in different environments, different settings, and even on different embodiments. So for example, with the mobile robot that you see at the top right corner. And then we are able to actually compare MolmoAct across 5 different VLA policy, also including some of the world models, for example, Cosmo policy. And we found that MolmoAct is actually able to get really good performance in terms of solving some of these tasks. And these are, as I say, it's been blindly evaluated. So and it's evaluated across 50 trials. So really doing a comprehensive understanding of MolmoAct's performance and capability when it comes to this kind of quick adaptation to new tasks. And beyond that, we're also interested to look at the quality of trajectory because at the end of the day, if you have a policy that's always jerking or is shaking, it's not smooth, it takes the longest path to actually get the task done, or if it collects a bunch of different objects in the environment while trying to do that, that's ideally not what you want. So in that context, we use this benchmark called Robot Eval, whereby they look beyond just successful metrics, whether did the task succeed or not, and that's what we have been using, but rather going beyond that and look at metrics that doesn't measure success. So in this case, it measures like shortest path length. It matters how much is the jerkiness in the motion as the robot does this task. And we found that MolmoAct is actually able to have really high quality trajectories as compared to some of these baseline VLAs. But of course, the plot on the right is sort of normalized. So at the end of the day, I mean, there's still a lot of room to improve upon. And one of the really unique capability about MolmoAct is also this thinking ability. So one of the things that we took back and feedback upon about MolmoAct 1 is that this reasoning trace is taking too long because it slows down inference significantly. And we do realize that actually you don't really need to reason in space at every time step. And you also don't really need to reason in space for every patch of the image. So the thing we developed is called this thinking model. And the idea behind this thinking model is that we still use the VQVAE to generate these depth tokens. But what we do is that instead of predicting the whole depth token of the entire observation, we train the model to adaptively predict depth tokens only on patches that it thinks it matters for the relevant task for the next time step of action denoising. And what it means that if you look at this observation, you could think that for every action it takes, the model only predicts the depth token for a certain region that it thinks it matters, and then condition on that to sort of connect to the action expert to predict the next actions, and then do that same process over and over again. So now you are doing much faster depth token prediction, and this gives that kind of natural adaptive nature. And one thing we realized that is when we look back and evaluate on Libra, which is the simulation that we used in the first version of MolmoAct, we found that with the thinking model, we are actually able to achieve much higher performance as compared to the regular model that MolmoAct2 was used for. I think at the end of the day, I think so that sort of concludes the whole, comprehensive evaluation that we have done from more of an academic point of view to do our due diligence to investigate how good is MolmoAct2 as a generalist model so that the community can sort of build on top of it. But what's really rewarding personally for myself is that in just less than a week since we released MolmoAct2, you could see so many people are actually building on top of it. People are deploying MolmoAct2 out of the box. And this really shows that, robotics foundation model is meant to be made accessible and open to the general public so that more people can understand, can diagnose, can inspect, and can continuously build on top of it. And hopefully that will eventually reach the ChatGPT moment of robotics where, everything is sort of, pushing the field forward. Yeah, and I think this is my collaborators. And then I also want to take a bit of time to just share that, I'm joining NUS Computer Science, and I'm actually hiring people to join my group, Magic Lab. And we're hiring, and it's fully funded. We're hiring PhDs, RAs, and postdocs. So feel free to reach out. Yeah, thank you. I'm open to any question. I know I talk a lot. But yeah.
Thank you for the wonderful talk, Jiafei. So now we can have some discussion. So feel free to just unmute yourself and ask questions.
I have one question
Yep.
regarding like VLA, how can we ensure the safety? Like, suppose I have any open source VLA I am deploying and fine tuning is working, but I'm not sure like the output action will be safe or no. Like, how can we ensure the safety in robotics? Any
Yeah,
idea?
that's a really great question. So I think I don't need to jump to any slides. But anyway, I think the short answer is that I think before MolmoAct, I think a lot of times people have the same question, right? Because when you're looking at an open source model, that's just purely open weights. You don't really know what goes underneath the hood for the data that was used to train. And secondly, if the model just taking observation and output action, there's no this kind of intermediate, steps that tells you whether is the model even doing something right. So with MolmoAct, we're able to output this kind of visual sketch that you could sort of visualize it before you execute the action. So I think in the more robotics context of like raw system with like RVers, you can sort of visualize the planning trajectory ahead of its time. Correct. In the same context for these VLA models, that's what we're trying to do in MolmoAct, the first version. And then in the second version with this adaptive tab, you could also diagnose the model before you actually execute the action. And at the same time, because that's why I'm trying to push forward for this notion of fully open science VLA models, is that you want to let people know exactly what is going underneath the data that is used to train. And then that helps you to ensure that safety, is sort of met. And also at the same time, you could also measure the kind of one thing that we also try to measure is the confidence level of some of these action being predicted. If there's a lot of uncertainties in the model prediction, then you might ideally not want to execute these actions. Yeah. So I think that's one thing. Obviously, there's a lot more work that has to be done in order for us to sort of reach that point. But at least I think open science models were able to sort of enable some of this capability.
Thank you.
I
Any
had a
more
question.
questions? Yep. Go ahead.
Doctor, thanks for the great talk. So I was just wondering, how would this idea evolve in the future? Like, how do you see this progressing in terms of, say, the future research direction you want to work on?
Yeah, so I think I mean like today's context in this kind of robotics foundation models landscape, I think people are looking at not just the way how data are being collected. So people are looking at human-centric data, ego-centric data, but I think there's also a focus on looking at what's the right backbone for robotics foundation model. So right now in this line of work or in this line of VLA work, people are building on top of a language model backbone. And then more recently, people have been building on top of like I guess like a world model backbone, which learns that kind of dynamics on pixel level. Correct. So in this case, I feel that is this both the right backbone for actually training a robotics foundation model? I can't say for sure, but I do think that humans, or if you take or sort of draw inspiration from how humans learn, I don't think as a child you're able to interact with the world having understanding of language. Language comes after a certain point. You are able to interact with the world without having language. And secondly, are you consistently imagining future states, of the world before you act? I don't think humans does that intuitively. So if you look at how humans are, learning how to act in the physical world, we have this really great, body that we have. That's the hardware. But at the same time, it's also we are having this kind of continuous stage of learning. So we started with just ability to sort of interact with the world without understanding language. But then towards a certain point where we have this creativity, we are able to sort of imagine future state of the world. And then towards when you are at a certain level, you're able to understand language instruction. You can follow instruction pretty well. You can then also act accordingly. So I think there should be these kind of stages of learning. So I think that's something that I'm really interested to look into. And obviously, by doing this in this way of continual learning, you are able to do more efficient learning because there's only so much data you can collect in the physical world. And it's not scalable to just, bet on collecting data. Yeah.
Understood. Thank you.
Any more questions? Yeah.
Yeah. Hi. Oh, it was really good talk, and I'm really interested in like vision language model and the vision language action model, and then you apply that into robotics. But one thing that I noticed is even though like vision language working fine for one specific robots, like typically from Gemini Robotics, but then like if I want to use the same model for my robot that I'm working on right now, which is not completely different from the Gemini Robotics, and the joint is different, like the range of the movement is different. So like it's really hard to integrate the same model into different robotics that I'm using right now. And another thing is, I wonder how you think to solve this problem. Um, so for example, I'm currently working on the social robotics and then deploying the social robots for the pediatric therapy centers. But one thing is I can't generate like robot integrated therapy activities like very scalably, like in real time. But then the problem is because it's for children, I want the robots to perform the gestures, the right gestures for corresponding to the sentence as well. But then the humans can do in real time, and then we can think about what's the right gesture. Oh, this story is about something, and then this sentence or this vocabulary has this type of emotional states, and we can make the gestures accordingly. But then like visual language action model currently doesn't have such things. So I wonder if is there any way, or do you have any ideas about solving the problem?
I see. I think so. I think you have two questions, right? So the first question is the embodiment problem. So I think
Yeah.
yes, right now there isn't, like all these generalist models are trained on a bunch of embodiment. You don't expect it to work on embodiment that you had never seen before, correct? You have to do some level of adaptation or fine-tuning or whatever, correct? So that is one of the first point that you brought up, which I think in the long run, I think what is actually missing is this co-evolution, which is that I think ultimately, a lot of times when we are working on robotics, is that we are always trying to improve models, or you can think of improving the software side of things and the hardware side separate from each other. So I don't think that makes sense. I feel that these two things have to be sort of co-evolving. You, how you build your software should also be informed by how you build your model. How you build your model should also inform what kind of hardware you want to build. So I think this is one of
Okay.
the fundamental gap. I mean,
Yeah.
you can see this everywhere. Like US is building some of these really great generalist model, but US is not building hardware. There's no robots that's like built at scale here, correct? But whereas China is building a lot of this hardware, but they're not really building like models. So I think only when these two things can come together, I think that will give you the most optimum outcome, like in my personal view. And then obviously, and the second problem I think is really like as of now with this kind of generalist model, I think the use case is not as what we think, as you can deploy it everywhere, and I think a lot of times you look at this is that there's no human, correct? Like if you think about it, all these models that is being deployed, all these generalist model, there's no human involved. What? So I think maybe there is also an angle to look into is like what could potentially be a more human-centric robotics foundation model. I think that's some of the expect, right? Because at the end of the day, you don't want this robot to just work alone at one side of the room and then doing some mundane chores without any human present. So you still want to be able to have human present. You want to be able to ensure that how will some of these models interact with humans. So right now we are sort of extracting out this human presence from this entire problem statement completely. Yeah.
So just back to the first question. So your point is if I want to use a model, then I have to first I have to fine tuning the model for my specific robot and then make it work for that specific model because we don't have like a general foundation model that works for all the robots right now.
Exactly. So that's the problem right now. But ideally, the goal here is that what we want to try to achieve is that when you have a pretty strong base model, the adaptation phase can be very fast. It could be just you teaching the robot one time or two times, and then you should be
Okay.
able to generalize adapt. So
Okay.
that's like the ideal scenario, right? I mean, obviously we are still far from that, but ideally we want to be in that state. So that could
Okay.
be one way. Another way is like there could be more research that's going to go into finding the right representation that's more that can be able to unify across different embodiment. So that could be another perspective or like another angle that I would say that we could potentially look into. Yeah.
Okay, thank you very much.
No worries, yeah.
Okay. There's like one question in the chat from Ajit who says that could you comment about the use of VLA, VLMs in manufacturing? For example, if a VLA is fine-tuned to assemble iPhones, is there a way to use the embodied data set of assembling iPhones while not allowing the secret recipe from leaking into the base policy?
Sorry, there's a long question. Let me.
Yeah, I mean, you can also maybe
Yeah.
look at.
Quick comment, Patrick is fine-tuned. Oh, I mean, I think that's the part, right? Because at the end of the day, I mean, like, it really depends on how you are using some of these policies. So obviously, at open weight level, if you fine tune and if you keep everything customized to your own setup, then you don't publicly release your checkpoint or anything. Then there's no way you can sort of leak out. But obviously, if there is companies or generalist startups that what they try to do is that they try to do an API call, then that might not be most ideal. That means if it's an API call or API layer, then you don't really know what's going to go, what happened to the data they use. So at the end of the day, I think you can look into that's why I think like with MolmoAct2, where it's fully open source, it allows you to actually have a better understanding of more transparency in terms of what is underneath the hood. And if you know what's underneath the hood, then it sort of prevents this kind of thing from happening. So I think there's another line of work in I guess like in the space of AI tool, which we look at training LM models that's privacy focused. So with like FlexOmo, it looks at how do you ensure that data doesn't propagate backwards into the model or sort of like keep confidentiality of this model. So I think there is work on that, but right now I think people have not really reached that point yet. But I feel that this is a very important safety measures that is critical. Yeah.
I have a question. Is it fine? I'm beware from the time.
I think it's fine.
All right, cool. I'll just wrap it up really quick. That was a great talk. Thank you for that. And it's a two-part question. It's most commonly asked around the physical intelligence community. So the first one is MolmoAct2 is heavily dependent on visual backbone, I guess, and the most frequent point of failures in VLA models are the visual occlusions and blind spots. So how do you handle that? And the second bit is about the blind obedience and physical hallucinations. Most VLAs, including MolmoAct2, are heavily optimized for task completion, right, rather than a physical feasibility. So how the robot know what's the actual physics behind the objects, like whether it's a clumsy paper cup or whether it's a glass cup.
I think you're muted, Jiafei.
Sorry, the first question, can you maybe say that again? There's two questions here. Okay, do
Sorry,
you
the
mind?
first one, yeah, I'll just go one by one. So the first one is the visual occlusion, like the most frequent point of failures in VLA or when the robot's own arm or gripper blocks the camera view, right? So how is it being trained? Because it's kind of like following up on previous answers as well. So how do you handle the blind spots?
Yes, great question. So I think to answer the first question, I think that obviously today's VLAs are just training with like perception data, right? So it's like you think of it as perception and action, right? So you have an observation, the robot sees, and the action. But I don't think that's the final form factor. In fact, I think with this kind of perception and action loop, you can potentially solve like I think like 90% of the manipulation tasks in this kind of VLA models. But there is going to be the 10% that you can't solve. And this 10% requires you to incorporate like different sensors like tactile, force torque sensing. And then these are things that sort of covers the point we just mentioned, which is that if the like humans sometimes you can act without even seeing, like without perception from the visual side. So I mean tactile is still some perception. But anyway, yeah, so I think we need to sort of incorporate this. And I think this is an active line of work that people are looking into how do you build these kind of multi-model sensors into these large scale models. Then obviously the harder part to do is that there is an imbalance in the amount of data. So if you think about it, robot data is probably here, and multimodal data could be way higher. the kind of data that you have that incorporates some of these sensors could be really low. So I think this is one of the bottleneck right now, but I feel that people are at least moving towards the area and seeing that the importance of this, right? Because there is just some tasks you can't do. Like for example, if you have an avocado, if you don't touch it and measure the amount of force that you apply onto it, how do you know whether avocado is right? There's no way you can do it. So this is one of the bottleneck. Yeah. And also, what's the second question?
Sure, that's a great answer. Thank you. The second question is more towards the physical hallucination bit itself. So I do believe MolmoAct2 runs an implicit world model, but how exactly does it understand the physical feasibility? Because from my understanding, it's more trained towards the task completion rather than the physical feasibility itself. So
Yeah,
yeah.
Yeah, this is a good question. So, one of the things that we did, obviously, with the what you call that, with the MolmoAct1 is that in my example, I showed that the model is able to predict this kind of visual reasoning trace. And if today you ask the robot to grasp an object that's so far away from the ro from the from where the base of that robot is, it will not actually generate you that line, or you will generate a line, but the line will be force short. Correct. That's because I think it learns that kind of kinematic feasibility from the data. And the way we sort of project it into this visual reasoning trace allows people to realize that, okay, this is not feasible. Correct. And then you don't need to act accordingly. Whereas in most contexts with general VLA models that just takes observation and output action, there might still be action, but you realize that the robot can never reach that point because it's kinematically not feasible. So I think this is one of the things that we're trying to do with MolmoAct1 to tell people that, okay, you sort of hit that kind of kinematic infeasibility whereby now your model is not able to reach that point. So you should not, like you should not continue, trying. I think this is one of the things that we realize. And to answer your question, yes, it really comes down to the amount of the kind of data that has been trained on. I don't think it has a sense of knowing its own embodiment, but at least it's able to sort of draw connections that, okay, given this observation, given this robot tag, what is the kind of action space I could potentially work in. Obviously, you will not be able to generate a delta or any factor, delta that is out of the way, out of the kinematic feasibility of whether the robot can reach. So that's the one thing. But they will still try. So I think this is one of the bottleneck with this kind of closed source VLA models out there.
Thank you so much. That's great answers.
Okay.
Hi, Dr. John.
Yeah, hi.
Yeah, thank you for the great talk. I really have two quick questions. So the
Yeah.
first one is you mentioned that MolmoAct right now have like intermediate visual plan, and I'm working on semantic safety. So I just want to know, can we treat this visual plan as a semantic object for safety verifications, or should we only verify the final actions on low level? And the second one is kind of linked to this, like for all the failure cases of MolmoAct, does it fail most often on the wrong depth understanding, or does it fail most often on waypoint planning? Like, what is the most failure occur?
I see. Great question. So I think if for the first question, I think you should definitely not just verify the action, because by the time you sort of verify the action, you have to take the action. So I think one of the things to talk to some of my friends who work in humanoid companies is that they always have a concern that how does people know whether the robot is safe, especially when you deploy a generalized model, right? It could do anything. And these things could be really out of distribution from, like a small thing could change. I give you an example, like the early days of robot learning, people actually collect data and test data at the same time of the day, just because that you're fit into the distribution. So if let's say something small change in this room and you're not able to sort of diagnose or sort of visualize this kind of intermediate trace and you execute the action, then that will have catastrophic impacts, right? So in that case, I think you should definitely use Momo as intermediate reasoning trace to sort of visualize it before you execute the action. If let's say if it's a task that is like safety critical, or like if there's humans involved. Correct. But even let's say if it's just a tabletop task and there's no human involved, it's okay if the robot bumps into it. I mean, like this is like still open research. And I think, sorry, can you recall, okay, repeat a second question?
Yeah, like for all the cases that MolmoAct fail, like where will the most failure occur?
I think the most failure occur based on our analysis is really lies in the depth token, the perception token. Because as I said, the perception token is because a lot of robot data today out there are not capturing this depth measurement. So we have to rely on distilling a depth anything model. So, and that's pseudo depth. So the problem about pseudo depth is that, it doesn't give you that kind of level of granularity as metric depth. So the token that's generated are also relative, depth, right? So in that case, then how do you ensure that in, let's say, if two objects is relatively really close, but then in reality, there's still some distance, and that could not be captured by the kind of depth token that's generated, and then that could cause some kind of confusion in terms of which object you should condition on. Yeah.
Thank you so much.
Okay, I know there are a couple of more questions in the chat. I would maybe ask people to join our Slack channel, and then we can continue the discussions there because we've already exceeded the time by 12 minutes now. But again, I would really like to thank Jiafei for taking the time to present your work. It was a great talk. And also everyone else for joining this session. And keep tuned at our website and our LinkedIn to hear about the next talk, which is happening soon.
Thank you for having me. And then if anyone who have a chance to try out the model or have like any one of these three embodiments lying around, love to please share with me. Yeah.
All right. Have a good morning, evening, night, everyone, wherever you're joining from.
Thank you, everyone.
Thank
Okay,
you.
bye.